When dealing with inverse matrices, invariably, at some point or another, we have to talk a little bit about determinants. Um, I explained how to find determinants, 2x2 determinants and 3x3 determinants in a different video. So I want to um, tell you where to find it. So to find how to find 2x2 determinants or 3x3 determinants, you can go to the video 52601. Very brief introduction. Very brief introduction of matrices and determinants. If you just want to look at determinants, start at 7:50, 7 minutes 50 seconds, and that's where you're going to start seeing the determinants. So if you are in YouTube, what you can do is just type in 52601, probably just a couple words such as very brief. You don't have to type the whole thing, and you should be able to recognize my video from there. So when we get to talk about determinants, I'm going to refer you back to this video, 52601, where we introduce how to find determinants. The other thing I want to do before we start talking about the inverse of a matrix is proofs by contradiction. Proof by contradiction. We use this extensively in mathematics. It's well established, it's well known. I take for granted that everybody knows what it means, which is not necessarily a good thing. It is not necessarily a good thing to take that for granted. So I just want to make sure we understand what a proof by contradiction means. So we want to prove that something is impossible or doesn't happen, for example. So the way we can start is by assuming it is possible. So a proof by contradiction, in a proof by contradiction, we start by assuming something exists. Something, it doesn't have to be that something exists, but something, just plain something. Okay, we start by assuming something. And we have to make it very clear that we are assuming that is so. And then we follow consequences of that. This arrow that we use in mathematics means implies. So that implies, another thing that relies on this, another statement, which implies, so we can label that as a statement 1. And then that may imply statement 2, which then could imply a statement 3. And this continues for a while. This could be very, very long or very short, and then we continue this way until we get to a final statement end. Okay, we don't know how long this chain could be. It could be just one link, or it could be 30 links, or who knows. But if those statements are constructed very well, very carefully, and the last one of those statements happens to be a contradiction, that implies that our assumption, our starting assumption, is false. And that is what we call proof by contradiction. So we have to end up with a contradiction. So this last statement, whichever it is, has to be a contradiction, comma, a contradiction. Something that is irreputable, that we will know for sure that this is completely, absolutely false. It is not a matter of opinion. It will be a matter of fact that this is false. And that would cause that this consequence is false, and the chain will go backward until we get to this point. But all the links have to be carefully constructed. Um, a proof is as good as its weakest link. So if any of those links is weak, is not really a proper link, then the whole thing falls apart. Then there's no proof. Unfortunately, with proofs, um, there is no, technically speaking, there is no partial proof. It's a proof is either correct or incorrect. Um, I suppose we can reduce the statement. So a proof could reduce a statement to some cases, but not, perhaps not all the cases. Anyhow, again, and we will probably talk about this again um, when we get to the impossibility of finding uh, inverse matrices. But I want to make sure we understand this line of thought, this thinking, in which again we assume something, some statement. Actually, this starts with a statement, and then that has a consequence, which is another statement, and the ultimate consequence, if we follow a particular path of or line of thought, will be a contradiction. If that happens, that means that the very first one uh, of the statements we made is false. We start by assuming something, and that's something that we would be assuming. I would call it statement zero. So we have statement zero, statement one, and so forth. Uh, yeah, yeah. Okay. So now we can start talking about inverse matrices properly. So um, only square matrices have inverse matrices. So we're going to assume that all our matrices involved are going to be square. So assume all matrices are square. So that is my shorthand for writing square. So assume all matrices are square. So what is the inverse? Oh, before we start with an inverse, we may not talk about inverse without talking about identity. First, we got to talk about the identity matrix. So, and I think we have explained this before, but let's just make sure. So there is a 2 by 2 identity matrix. We can label it as I2, although oftentimes we omit or 2 by 2 to be even more specific. Oftentimes we omit this. It's understood by the context what the size of the matrix is. So the identity matrix is this one, a 2 by 2 identity matrix. Why? Because if we multiply by any matrix A, B, C, D, 1, 0, 0, 1, okay, that's going to give us A and 0, nothing and B, C and 0, nothing and D. So remember, yeah, we're doing columns. So this picks the first row, this column picks the first row, and this column picks the second row, and you just copies it over. And if you put it on the other side, we're going to end up with the same thing. So this is the identity. Why? Because when we multiply that matrix with any other matrix, we get back that other matrix. So that is called an identity. That is a special matrix. Now, we have an identity for each dimension. So a 3 by 3 matrix would be a 3 by 3 identity matrix. 3 by 3 would be, of course, the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And I think it is clear, but let's just do it real quick. A, B, C, D, E, F, G, H, I multiplied with 1, 0, 0, 0, 1, 0, 0, 0, 1 will give us, again, A and nothing, nothing and B, nothing but C. So we got A, B, C. I'm trying to think. Okay, so I keep the same row and I go down the columns. What if we do it the other way? Keep the column and then I'm going to go down the rows. So I think that's going to be a little more efficient because we have take the A and nothing else, take the D and nothing else, take the G and nothing else. So D, G. All right. And as we use this column, we're gonna pick up the middle term. So nothing B, nothing. Well, we did that. Nothing E, nothing. Nothing H, nothing. And then we do the same thing here. Nothing and C. We did that. Nothing and F. Nothing and I. There we go. So we want to convince ourselves that this is the identity, because when we multiply by any other matrix, we're going to end up with the same matrix that we started with. Not with the identity, of course, but the other one. And if we multiply on the other side, the same thing will happen. So before we can even talk about an inverse, we have to have the identity, because the inverse is relative to the identity. Yeah, we cannot have an inverse. We cannot have a conversation about inverses without an identity. So inverse, in a way, it's kind of like the other way. The other way of what? Where's the middle? That's kind of where this is going. So the identity is the middle, so to speak. Okay, so now we can define the identity. So an identity of a matrix, and we're assuming that all our matrices are square, an identity of a matrix A labeled like so, with a -1 as the exponent. So that means the inverse of A is a matrix such that A inverse, when we multiply them together, gives us the identity. And here's why it is handy not to have an index, a size, because we just want to give this statement in general. If this is a 2 by 2, that will be 2 by 2, and so the inverse has to be 2 by 2. If this is 3 by 3, that has to be 3 by 3, and the inverse has to be 3 by 3. If this is 4 by 4, the inverse has to be 4 by 4, and that causes this guy to be 4 by 4, etc. So 5, 6, I can keep going like that. So this is a general statement of what an inverse is. Now, you can define anything you ever wanted. So for instance, you can define a unicorn, a horse with a horn on the forehead. And I don't know if unicorns fly or not, but you can define it as one that flies and one that doesn't fly. You can define it any way you want, but that doesn't imply that it exists. And I'm not saying they don't. I'm just saying defining is independent of existence. You can define something without existing it. You can describe something which does not exist. So yeah, we can say this guy does this, but that doesn't necessarily mean that it exists or that it exists all the time. It may exist sometimes. And that is the case with the inverses. they exist sometimes and sometimes they don't exist, depending on the matrix. So if the matrix has an inverse, um, we label it as invertible. If it doesn't have an inverse, then we can label it as singular. So invariable means that it has a matrix, rather, that it has an inverse, and singular means that it doesn't have an inverse. The other thing to notice is that um, if we have a right inverse, we also have a left inverse. Maybe we should write this down as part of the definition. And A inverse A is also the identity. So we have to have both. This is an and. Yeah, and. So this and that have to happen. Yeah. The one thing we can easily check, and I think we checked that in our previous video. This video is 70008. In 70007, we proved that if there is a right inverse and a left inverse, then they have to be the same. So that's why we put down the same thing here, because they have to be the same. Oh, in the definition, I did mention that I did use the article "and," which means that this article suggests there could be more than one. Um, in reality, there's only one. Part of the reason is this: yeah, if it's on the right, it's on the left, and if there's two of them, it's easily checked that they have to be the same. So let's state a fact. Um, inverses are unique. Yeah, they are unique. That means that there's only, if there is one, let's specify what we mean. So let me elaborate, which is very short. If they exist, then there is only one. Of course, for each matrix A. So if there's an A inverse, there's going to be only one. Don't look for a second one, because there isn't going to be a second one. That's a fact. It's proven. Yeah. So, but some matrices don't have inverses. If they do, there's only one. Some don't. All right. So we are talking about existence, uniqueness. Now, how do we go about finding them? How do we find them? Question mark. All right, let's actually come up with a problem. Let's say we have the matrix. So this is an example. 2, 1, 7, 4. And let's think about, I mean, you can look up at a formula somewhere in a book, and it will tell you, switch those two and put in minuses and divide by the determinant, and then you're all set. Yeah, but why? How? And so it is fruitful to figure out how we get this, and it helps us understand further things that we need to know in a class like this one. All right, so let's pretend we don't know what it is, CD. And the goal is to figure out what this matrix is, so that when we multiply them together, we get the identity. All right, so we have a system of equations. Well, we're going to end up with a system of equations. We're going to have, if we multiply those two matrices, we end up with 2A plus C. 2A plus C is equal to, okay, so 2A plus C is the 1. Let's do 2B plus D. 2B plus D has to be 0. 7A plus 4C, 7A plus 4c equals 0. And 7b plus 4d is 1. Okay, so we have 4 equations and 4 unknowns, a, b, c, d. Again, a, b, c, d. Well, naturally, uh, these are actually, it's interesting. We have 4 equations, 1, 2, 3, 4 equations, and 4 unknowns, a, b, c, d. But naturally, they are clustered into 2 and 2 in such a way that AC, those 2 equations are 2 equations with 2 unknowns. They only have A and C. So this is a smaller problem than all the 4. It's not a complicated problem in the sense that it's just 2 systems of equations of the same kind. Okay, so let's figure out how to get this. So one thing we've done before is the method of elimination, which we're going to do again here. So we're going to eliminate the 7 using the 2. So that means we have to put -7 or multiply. Yeah, let's do it this way. We're going to multiply this equation by -7/2. We're going to multiply times, because that's going to create a 7 here, which is going to cancel with the 7 because of the negative. So when we multiply -7/2 by 2, we end up with -7, and the a stays. When we multiply -7/2 with 1, we get -7/2 c equals -7/2. So we're multiplying the entire equation, this first equation, by -7/2. And what we gain by that, which seems rather complicated, is that then we can add the 2 equations together. This already has a negative, and we end up with, well, we can add those 2 equations. So of course, they're going to cancel out no a. This is 8/2 minus 7/2. Well, that is half of a c. Oh, and that is 0 minus 7/2. So that is -7 over 2. So if we multiply the equation, this new equation, by 2, we end up with 7, rather with c equals -7. Okay, so this entry has to be -7, apparently. And how about a? Where's a? A is here. So if c is -7, move it over, so we end up with 8. But that's 2a. We divide 8 by 2, so a has to be 4. All right, so this entry has to be 4, opposite of 7. All right, and then we're going to deal with this system of equations. There's 2 unknowns and 2 variables. Well, two equations and 2 unknowns. Interestingly, it starts out the same way. The pattern is the same. That's what I'm trying to say. 2, 1, 7, 4. Of course, because it came from the multiplication of this matrix. Yeah. So we can just repeat the procedure. Okay, so I'm just going to put down repeat. Except we're going to end up with 0. 0. Instead of multiplying 1 by -7/2, we're going to multiply 0 by -7/2. Yep. So at the end, we're going to end up with a half, not a c, though that was a c here, but here we have a d. Half d equals 1. which means that D has to be 2. So if D is 2, well, that has to be -2, but the only way to get that is if B is -1. So B equals -1. Okay, so it is neat to notice that we're going to end up with the same computations, almost. I mean, on the left, not on the right. On the right, we did multiply the 1, and adding 0 gave us this. Here we multiply the 0, and then we added 1. Okay, so it seems that the inverse, okay, so here's the solution. The answer, if we were looking for the inverse of 2, 1, 7, 4, its inverse will be A, B, C, D, except that now we know A is 4, B is -1, there it is, C is -7, and D is 2. Okay, let's see if that is true. We want to check. So 2, 1, 7, 4, 4, -1, -7, 2, because our goal is to get 1, 0, 0, 1. But maybe I made a mistake on the computations. Maybe I assumed something incorrectly. So it pays to do this, to check. So 8 minus 7, sure enough, 1. But don't just check that, because maybe the mistake happened on the second column or on the second row. We don't know. -2 plus 2, 0, if there's a mistake. 4 times 7 is, boy, that's a big number, 28. But then we are subtracting 28, so we're good. And then -7 plus 8, sure enough, that gives us 1. So indeed, this is correct. This is the actual answer. This is the inverse of the matrix 2, 1, 7, 4. It is 4, -1, -7, 2. Something that we should also notice is that we solve this equation for the whole entire matrix, but we could split up the problem into fewer problems. Well, we can split it up not into fewer problems, into more problems that are each one of them simpler. So sometimes we want to do this, 2, 1, 7, 4, and we want to find the vector AC that causes 1, 0. And then we also want to do this 2, 1, 7, 4, and we want to find the vector BD that creates 0, 1. Oftentimes we label this as little e1, and this is little e2. The unit vectors in the direction of x, the direction of y. If there's 3 dimensions, this is kind of misleading, because if we were in 3 dimensions, we will label the 3 vectors e1, e2, e3, but they are not the same as those vectors. Anyway, so we can split this up into 2 problems. Or we can consolidate. So this is one way to go. So before I do this, let me just show you. So this is another idea. We can split into 2, or we could consolidate the computations. So, or consolidate the computations into one matrix. And doing so is what is called the Gauss Jordan elimination method to obtain the inverse. So let's practice that one. So we are still doing the same example. We haven't gotten away from the same example. So Gauss Jordan elimination. We start with the matrix 2, 1, 7, 4, and next to it we put the identity matrix 1, 0, 0, 1. And what we want to do is solve for A, this A, and C. So that's C. We wanna have the very specific A and C, but that's gonna hit two birds with one stone, because we're gonna solve this vector for this vector, and we're gonna solve for this one. The two of them in one computation. See, we did two computations here. We did this and that, but the process was a repetition of the same thing. So instead of doing that twice, we're going to do it once. Let's go ahead and show how we go about it. Okay. Yeah, this is a little different than just elimination. So the Gauss Jordan elimination is more than just elimination, because in elimination we still use back substitution to get to the solutions. With the Gauss Jordan elimination, the solutions are already going to be there. All right. So to make things easy on us, we divide this row by a half. I meant by that, I misspoke. We divide by 2, which is the same thing as multiplying by a half. So we're going to multiply. We're going to obtain a new matrix, row 1 by a half. There we go. Multiply by 1/2, and we're going to obtain a new matrix. So that's going to cause this to be 1, 1/2, 1/2, 0, and keep the second row the same. Then we're going to subtract. We're going to multiply this by 7, and we're going to subtract the second row from that multiplication by 7. But we're not actually going to actually write down the multiplication by 7. We're just going to do it. Yeah. So this is called the pivot, and we're going to use that to subtract here. So subtract 7 times row 1 from row 2. All right, so the first row is going to remain as is, and we're going to subtract from the second row 7 times that. So 7 minus 7 is 0, which is our goal. We want to end up with an identity matrix on this side. And the reason is because we're solving for A and C. So right now we are beginning to solve for A and C. Anyway, 4 minus 7 times that. Remember, we're subtracting 7 times the first row. So that is the same thing as 8/2 minus 7/2. That's still a half. 0 minus 7/2. 1 minus 7 zeros. Okay, so this column is good. We can multiply this row by 2 to get a 1 here. Multiply row 2 by 2. So we have 1, 1/2, 1/2, 0, 0, 1, negative 7, 2. Okay. And now we want to have a 0 there. Remember, we're solving for A, C, B, D all at once. Okay. So now we want to end up with a 0 here. And the way to do this is to we're going to subtract a half, because we want to match this coefficient using the 1. So we want to subtract half of this from row 1, half of row 2 from row 1. Okay. And we really want to proceed by columns. This is an algorithm, a process of steps, and we want to go by columns. Because if we don't go by columns, if we start going in all different directions, let's say there was a number here still, and we wanted to get rid of this guy. Well, that's going to mess up our coefficient here if we start adding things, second rows into first rows. So that's why we want to end up with a 0, so that when we add, we don't have anything to add. This is not going to change. We're not going to mess up what we already did. So that's why we want to end up with zeros. Make sure to practice this. This is, as you can tell, this takes time to do. It's not just like multiplying two numbers. It is a longer process. This is not just like using the quadratic formula and boom, we get the answer. No, 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 no. It is much more work than that. And don't use a calculator. I mean, yeah, use a simple calculator such as this one, but not a scientific calculator that can actually invert the matrix. You can use that to check your answer, but not to actually invert it. Anyway, so 1 minus half of 0, still 1. Half minus half of 1, 0. 1/2, this is a little more confusing. 1/2 minus negative 7/2, because we gotta divide by 2. So 1/2 minus negative, okay, that's gonna be plus. Okay, 1/2 plus 7/2, there we go. 1/2 plus 7/2, that's 8/2, which is 4. 0 minus a half of 2. Okay, and the second row remains as is, negative 7, 2. Okay, so we have solved for A, C. No. This is confusing. We're solved for A and C and for B and D. Yeah. So see, we are reducing our work. Instead of doing the computations twice, we're doing the computations once. But remember though, originally, we were supposed to do this problem twice, 1 and 2, one time here and one time there. So we would be solving for A and C and for B and D in 2 separate problems. But because the computations are the same, this is a repeat, because the relationship among the variables is the same, 2 of one plus the other, 2 of one plus the other, 7 of one plus 4 of the other. Then the process is repeated. So when we get to this point, it looks like, oh, which one is A? And no. This is double dipping. So those two guys represent A and C on one hand, but they also represent B and D separately, because we are double dipping. We're using this process once instead of twice. Now, if we had a 3 by 3 matrix, we would have to use the process 3 times, or a 4 by 4 4 times. Yeah. So this gives us, now how can you tell which one is A and C? Well, there is A, C, and then there is B and D, all consolidated into one matrix. And by doing so, this is already the inverse. So this is the A inverse. Okay. So there. That's what happens. That's how it happens. We are doing 2 in 1. Example 2. Let's try to find the inverse of 1, 1, 1, 1. Okay. So I'm going to do only half of the problem. Now, so let me divide this and say we're gonna find inverse. Okay. Now, finding the inverse algebraically in algebra may assume that there is an inverse. So when we say, well, one of the things we want to be able to do is come up with, if we multiply with AC, we want to be able to end up with 1, 0, because that is the first column of the identity matrix. So among the things we have to do this. Now, when we write this down, there is an implication, or there's an assumption when we are writing all of this down. Okay, we assume 1, 1, 1, 1 inverse exists. Okay, so that is an implicit assumption because, and this is what is called the analytical method, when we assume something exists, and then we try to find, as we go through the process, the nature of what we assuming it exists, then we're solving the problem. We're figuring out what it is. That's actually what happened here. We're using the analytical method way at the beginning here. Okay, so if we want to find the inverse of this matrix, as soon as we wrote this equation down, we are assuming that such inverse exists. And by doing this, we are trying to figure out the nature, the concrete nature of the inverse. So what is the actual value of A, B, C, and D? But again, we're assuming such thing exists. So there's an assumption that is implied here. We're assuming that a solution exists. And then we are finding its nature, the nature of the solution, rather. So here, when we write this down, we're assuming, okay, if it did exist, we would have to fulfill this. All right, so then so if it did exist, then this part would be true. Okay, well, let's write a little more. Say the inverse is A, B, C, D. Okay, so we're making this assumption. Okay, as a consequence of that, if such inverse does exist, then we can get to this statement. So this is the assumption or statement 0. Whereas when we say an inverse exists, we're saying something. We're making a statement. Exists. And we're just gonna put letters for the numbers on the matrix. So this, we can label this as statement 0. A consequence of that statement is this. So this could be our statement 2. Rather, 1, statement 1, statement 0, statement 1. Okay, if this is so, then that means that A plus C, so then we can arrive to a new conclusion. A plus C is equal to 1, while A plus C is equal to 0. Okay, so now we got a new statement. I'm going to call this statement 1, statement 2. This was the original statement 0, ground 0. All right. Now this is a statement. This is something that we are deducing from here. Okay, if this is true, we know we have what is called the transitive property of equality. Of equality. It says that if, well, with letters, it says that if, let me just write it down on a different page. So that, well, I can just write it here. It says that if A is equal to B, comma, and B is equal to C, then this guy is equal to C. The equation transfers. So we can read this backwards because there is the symmetry of equations too. So if 1 is equal to A plus C, and on the other hand, we're saying that A plus C is equal to 0, by the transitive property, we're saying that 1 is equal to 0. So we can label this as a statement 3. Okay, that's a logical statement, and we're using proper logical explanations of why we are arriving to this conclusion based on those two statements. So this is a combined statement. There's an and in between. It is a compound statement because there's actually two of them. This is one statement, really, one matrix, although we can split it up into two. Okay. But we notice, we look at this and we say, oh my goodness, this is false. Yeah. And then we notice without any doubt that this is false. Or another way to state that is this is a contradiction. A falseful is called a contradiction. Contradiction. Yeah, it cannot be that 1 is equal to 0. That's now, I'm not saying that the statement doesn't make sense. The statement does make sense. It just happens to be false. Today, for instance, is September 8th, which is Tuesday. If I say today is Wednesday, that is a perfectly well-constructed sentence. Today is Wednesday, period. You know, and I capitalize all the letters that have to be capitalized and everything, and the spelling is correct, and so that's a well-constructed statement, but it is a false statement. So the fact that we can construct perfectly good statements doesn't mean that they are false or true. You know, that has to be judged, that has to be studied, analyzed. So this is a very good statement. 1 equals 0. There's nothing wrong with it. As a statement itself, it happens to be false. That means that through this chain, our assumption that, and what was our assumption? That an inverse exists is false. Consequently, by this chain of statements and by proof by contradiction, we can state that the inverse of this guy does not exist. So our conclusion, so by proof by contradiction, 1, 1, 1, 1 has no inverse. Because if we assumed it did, invariably we arrive to a conclusion which follows with another conclusion, which follows with another conclusion, but this conclusion is false. So that means that this guy has to be false to start with. We cannot assume it is correct. I mean, if we did, we get to a contradiction. You know, and you can repeat this a million times. You know, so that means that cannot happen. It is not true. Now, you don't have to show the second column also fails to appear. All it takes is one contradiction. As soon as you get to one contradiction, you're set, you're done. Yeah, the proof by contradiction, you're done. And that creates a problem. So we're finished with this. This is the end of that. I just want to elaborate on the proof by contradiction. So if we make an assumption, which is statement 0, and then you get to a statement 1, and you get to a statement 2, and let's say you go to a statement 3, and this happens to be a contradiction. Oftentimes, math people use the exclamation to show, although that is used in many different ways. That's also the factorial. That's also the there was one other one. Oh, uniqueness too. So maybe scratch that. Um, it is used, but let's use another one that math people use instead. Anyway, so two arrows pointing to one another. That's a pretty good one. So two arrows pointing to one another, that represents contradiction. Okay, so an assumption goes to a statement, goes to a statement, goes to a statement, and gets to contradiction. One of the problems with proofs by contradiction, this is a proof by contradiction, this is the body of a proof by contradiction, is that sometimes it is not easy to know which one to follow. And sometimes there are more than one path. So for instance, we did follow the path of column number 1 when we proved that an inverse does not exist. So yeah, we went 1, 2, 3, and that was this was a contradiction. But what if we follow the path of looking at the second column? So then you got statement 1, statement 2, statement 3. So I'm getting lazy. Instead of ST, I'm using S instead. And then that is a contradiction. Now, you don't have to go through all of them because there's going to be many of them. I mean, you can elaborate once you have and don't continue once you have a contradiction, because if you add a 1 to both sides of this equation, you end up with 2 equals 1, which is again a contradiction, a falsehood. So a falsehood rather. So when you are doing a proof by contradiction, do one. There may be many. S1. Who knows? Maybe somebody's going to do all of the 2 columns at once, by trying to do the Gauss Jordan elimination. That would be a third way to do this. S2, and then you get to S3, and there's a contradiction. So there's many ways to get a contradiction. Just pick one, and that's it. Don't go any farther. Don't elaborate anymore, other than saying, well, this is false, and consequently, our assumption is false. And that's the end of it. Just like up here, by proof by contradiction, this guy has no inverse, because the assumption that having an inverse leads to a contradiction, that assumption is incorrect. And the other thing that I'm just questioning myself, what if we go into a path that doesn't seem to go into a contradiction? I think that happens. Yeah, that happens in math. It does happen. So you go to S1, you go to S2, you go to S3, and you go forever. Well, I shouldn't say forever because I don't know if this has been tested, but maybe the path doesn't give us a contradiction after a while. Well, that doesn't mean that this is not false or that this is not true. We don't know. We would have to prove it. Yeah. So this is the proof by contradiction. This is a diagram that explains proofs by contradiction. And we just use that thinking to show that an inverse does not exist. Now, that is sometimes, sometimes it is lengthy, but it's not necessarily bad. There are other ways to demonstrate that a matrix may not have an inverse or does not have an inverse. The one other thing I want you to please do as a student is to practice um, many matrices. Find the inverse using the Gauss Jordan elimination. Um, the thing to do would be to do a problem that is 3 by 3, and I'm trying to think whether that is it is the same process. Um, yeah, it is the same. Let's do one. I suppose we can do one. So let's say you have the matrix. So example 3. Um, so we want to find the inverse of 3, 1, 2, 5, 2, 3, 4, 2, 3. Whoops, I didn't mean to do that because I'm using the Gauss Jordan elimination. Well, I'm going to find the inverse of this. So the question is find its inverse if there is one. By the way, if you're trying to find the inverse and there isn't one, eventually you're going to end up with a contradiction. At that point, if you get to a contradiction, such as 0 equals 1 or something like that, you can stop and say, oh, because we arrived to a contradiction, the assumption that there was an inverse is false, which means that the matrix has no inverse. So trying to find the solution is could work in both ways. Either it does give us a solution, or it already works as a as a as a proof that there is no solution. Now, there's one requirement when we're doing proofs by contradiction, and I did say this earlier, but I want to emphasize it. Every step has to be correct, accurate, and correct. So every implication has to be pretty much double checked, because if one implication is not correct, then even if the last statement is true, we arrive to it by the wrong means, and consequently, the proof is not valid. Yeah, and proofs are either right or wrong. They're not really, partially correct. So we have to check every link of the chain of thought or the chain of statements. All right. So let's use the Gauss Jordan elimination. 3, 1, 2, 5, 2, 3, 4, 2, 3, 1, 0, 0. So we put, so we're going to, instead of finding a, we're assuming that we're going to find A, B, C, D, E, F, G, H, I. So instead of finding A, D, and G by matching with the first column 1, 0, 0, and then the next column here by matching with 0, 1, 0, and the last one by matching 0, 0, 1, and then we will have 3 systems of equations with 3 unknowns, each one of them, such as A, D, F, H. I think A, B, C, D, E, F, G, rather G. Um, instead of doing the work 3 times, we're just going to do it once. So we're going to find A, D, G, and then B. Well, I have to think of the columns. Yeah, I'm going to write them on a different piece of paper here. So we're going to assume that it is A, B, C, D, E, F, G, H, I. There we go. So when we end up with 1, 1, 1, and zeros everywhere else, we're going to find A, D, G if we match with this column. But if we match with this column, the 1, 1, 1, and zeros, we're finding actually B, E, H. And if we match the 1, 1, 1, and the zeros, with the third column, then we're finding CFI. So it's not like each one of those represents each one of those. No, no, no. We're using the same diagonal for this column, the same diagonal again for the second column, the same diagonal again for the third column, because the process is the same. Anyway, now I like to take some shortcuts, or I like to be a little sneaky about this. Technically speaking, the proper process states that we have to divide by 3. If we divide by 3, that will make this a 1. And then we will be able to eliminate those two numbers, those entries. But the problem with dividing by 3 is that we're going to end up with a third and 2/3 and a third. And that's going to start creating, and then we're going to multiply by 5. So we're going to end up with 5/3 and 10/3 and so forth. And the fractions are going to mess things up. So especially because we're doing this by hand. If we were doing this with a computer, no problem for the most part, because we can divide by 3 and the computer doesn't care. I'm just going to divide by 3. It'll just crunch the numbers, no problem. But because we're doing this by hand, and the expectation is that students are doing this by hand, then I'm going to try to avoid fractions only to avoid the complications. So one thing we can do is subtract this first row from the last row, and that's going to create a 1 immediately right here. And then we can always move that row back to the top. Yeah, because we're solving a system of equations. Yeah. So remember, we will be solving for ADE. So the first column represents the A no matter what. So even if it's down here, we will represent the A. Anyway, so we're going to take the third row and subtract the first row instead. So the first row is going to stay as is. 3, 1, 2, 1, 0, 0. Second row stays as is. 5, 2, 3, 0, 1, 0. And then we're going to subtract 4 minus 3, 1. 2 minus 1, 1. 3 minus 2, 1. 0 minus 1, negative 1. 0 minus 0, 0. 1 minus 0, 1. Okay. I probably should write the matrix first and then the parentheses after. Otherwise, they may look too short. It looks like a very tight parenthesis for this matrix. Anyway, eventually I want to put this on top. So the leading 1 should be on the upper left corner. But I cannot help to start. Well, let's do that first. So we're going to switch R1 and R3. Okay, so now I'm going to put the numbers first. So we got 1, 1, 1, negative 1, 0, 1, 5, 2, 3, 0, 1, 0, 3, 1, 2, 1, 0, 0. Okay, so we're still solving for A. This column represents the A because we're doing a system of equations. Just like A plus B plus, no. A plus D plus G, A plus D plus G represents this, is equal to negative 1, 5A plus 2D plus 3G is 0. Yes. And so forth. Anyway, so we want to clear this off, and we're going to take the second row and take away 5 times the first row. And that clears the 5 off. And then from this row, from the third row, we're going to take away 3 times the first row. I was pausing because I'm getting into row operations, but remember, we can achieve the same thing by multiplying on the left by a square matrix. And it is not a bad idea to think about how that square matrix looks like. I'm going to pause for a moment. That is kind of important. Let's not forget that those two operations can be achieved by multiplying by, okay, so negative 5, 1, 0, negative 3, 0, 1. So multiplying on left side. Yeah, because then I'm just double checking. Yep, negative 5. Yep, that will do it. And then negative 3 times this guy. Don't add it to that, but add it to the last one. Yes. So remember, we're doing, this is called row operations, the ones we're performing here, such as subtracting, swapping, and subtracting or adding multiples of one row into another row are called row operations. So these are row operations. But also think of them as multiplying on the left by a matrix. So keep that in mind. Okay, so let's go ahead and get our next matrix. Oh, so the first row stays intact. Second row, 5 minus 5, 2 minus 5, 3 minus 5, 0 minus negative 5. 1 minus 5 times 0, 0 minus 5. Okay. Third row, 3 minus 3, 0. 1 minus 3, negative 2. 1 minus 3. 2 minus 3, negative 1. 1 plus 3, 4. 0 plus 0, 0. 0 minus 3. Okay. I hope I'm not making a mistake, because then all of the people who are watching this video are going to say, he just messed one up. And then I have to go back and see. This is the problem of not doing this class live with actual students. If I make a mistake, let me double check. So 2 minus 5 is negative 3, negative 2. Positive 5, 1, negative 5, 0, negative 2, negative 1. 1 plus 3 is 4, 0. We're subtracting 3. Yep, it looks correct. And then we're going to continue with this. Okay, now we want this to be A1. 1. And one way to achieve that is to divide the whole row by 1/3, negative 1/3 rather. But again, that's going to create fractions. Now, I'm not guaranteeing that you're never going to see fractions. I'm not stating that. But I'm not saying that fractions are bad and should be avoided at all costs. No. I'm just saying, since I'm doing this by hand, I'm going to try to avoid fractions. But if I have to, I will. We will just do that. And I'm thinking, if I want a 1 to show up in here, because that will cause the other two entries in that column to simplify to 0 easily. If I want a 1 here, I could divide by negative 3, or we can add, or subtract rather, 2 of those. See, if we take row 2 and take away 2 times row 3, which is a valid row operation, which is also can be also represented by a multiplication on the left by a matrix, then if it achieves the goal and we are doing this legally, then we're good. All right, so 1, 1, 1, negative 1, 0, 1. Okay, and this is what I'm going to do. So those are 0, so they're not going to, this is not going to affect that no matter what we multiply with. Okay, so negative 3 plus, rather, minus negative 2. Well, that's plus 4, and that causes this to be 1. But we just got to do the same thing across the board. Negative 2 plus 2. Well, what I did here is negative 3 plus 4. Negative 2 plus 2. Oh, that's nice. Negative 2 plus 2. 5 minus 8. 1 minus 0. Negative 5 plus 6. 0, negative 2, negative 1, 4, 0, negative 3. And let me double check. 0 minus 2 of those. Negative 3 plus 4 is 1. Negative 2 plus 2 is 0. 5 minus 8, negative 3, 1. Ooh, good thing I checked. 1 minus twice 0 should be 1. One minus twice 0, negative 5 plus 6. It's 1. Good. And then this remains the way it is. Okay. So we are getting closer. Now we want to get rid of this 1 and that 1. And we want to go, we want to make sure this column is completely done before we move on to the next column. Because if this column was not right and there was a number, non-zero number here, if we attempt to subtract row 1 minus row 2, well, that's going to create a problem here. That's going to mess up this entry if we don't have zeros everywhere else. So we're going to do row 1 minus row 2 because that's going to cause this entry to be 0. And we're going to do row 3 plus twice row 2. So twice that on top of that, that's going to cause this to be 0. All right, so we're going to subtract 1 minus 0, 1. 1 minus 1, 0, which is what we wanted. 1 minus 0, 1. Negative 1 plus 3, 2. 0 minus 1. 1 minus 1. Second row remains as is. There's no change on the second row. Last row, we're going to add 2 of those onto that. So 2 zeros plus 0, 0. 2 ones plus that, 0. 2 zeros plus that, negative 1. Negative 6 plus 4, negative 2. Yeah, we're adding, boy. So we're adding, I just want to make sure we're adding negative 6. So 2 plus 0, 2. 2 plus that is negative 1. Whoa. Okay. So we're going to multiply this guy by negative 1. So row 3, we're just going to multiply it by negative 1. So we end up with a positive 1 here. One, 0, 1, 2, negative 1, 0, 0, 1, 0, negative 3, 1, 1, 0, 0, positive 1, positive 2, negative 2, positive 1. And finally, to get rid of this one, we do row 1 minus row 3. You know, now that I'm thinking, maybe this method is, the method of having fractions is more efficient, because with the fractions, okay, so with the fractions, we need 1 step, 2 steps, 3. With the fractions, we only need 9 steps with the method of fractions. When we finish, we'll count how many steps it took us to get to this point. So 1 minus 0, 1, 0 minus 0, 0. 1 minus 1, 0. 2 minus 2, 0. Negative 1 plus 2, 1. Negative 1. And then we end up with 0, 1, 0, negative 3, 1, 1, 0, 0, 1, 2, negative 2, 1. So we claim this is the inverse of the matrix. Now, before we check, let me check this number of steps, because now I'm curious. I was trying to avoid fractions, but maybe there was a price to be paid. It took us 1 step. No, that is the beginning. 1, 2, 3, 4, 5. Oh, 6, 7. Actually, that wasn't too bad. I didn't know whether I was using more steps or fewer steps. Anyway, the claim is that the inverse matrix is this one. So we gotta multiply the original matrix for which we were trying to find the inverse, 3, 2, 1. I'm nervous, or rather 3, 1, 2, because if I'm wrong, I have to go back and see where the mistake is. So I'm very, very nervous. Okay. So 0, negative 3 plus 4. Yep, that gives us the first one. 0, negative 6 plus 6, 0. 0, negative 6 plus 6, 0. So the first column is right. So that means, yeah, the first column here is correct. Second column, 3, 4 minus 4, 0. 5, 7 minus 6, 1. 4, 6 minus 6, 0. Okay, so this column is correct. So if there is a mistake, it will be here. Negative 3 plus 1 plus 2, 0. Negative 5 plus 2 plus 3, 0. Negative 4 plus 2 plus 3, 1. Okay, so now we can say, so the conclusion is that 3, 1, 2, 5, 2, 3, 4, 2, 3 inverse is equal to 0, 1, negative 1, negative 3, 1, 1, 2, negative 2, 1. Once you have an inverse, you can mass produce solutions which involve those system of equations. So let's go on a little bit. Okay, so now what? What is a consequence of that? Well, let's label this as example 4. I think that was example 3. let's say you have 3x plus y plus 2z equals a number to be determined 5x plus 2y plus 3z, 4x plus 2y plus 3z. In retrospective, that wasn't too bad. And then you put any random numbers you want to put, such as 7, 6, 5. And you wanted to solve this system of equations. Well, those are these matrices. I mean, the entries, the coefficients are the same as the coefficients in this matrix, as the entries in this matrix. So if we wanted to solve, okay, so 3, 1, we can rewrite this as 3, 1, 2, 5, 2, 3, 4, 2, 3. X, Y, Z equals 7, 6, 5. So if we multiply the inverse on this side and on this side, let's write it as AX equals B. So if we multiply with the inverse on the left, those two become the identity. So we really have just the identity times X, or just X, because the identity times X gives us back the X. So all we have to do is multiply the inverse, which we found in example 3, with 765, and voila, there is the answer, because we already did the work in general. And that's the beauty of this. We don't have to redo the work. Once we do it once, that's it. Okay, so this is the vector X. So X, Y, Z is, okay, I'm copying the answer from here, 0, 1, -1, -3, 1, 1, 2, -2, 1, times 7, 6, 5. Okay. So let's just make sure this is going to be, well, 6 minus 5, 1. Okay. -21 and 11. That looks like -10. And 14 minus 12 is 2, plus 5, 7. So it looks like if you were given this system of equations, the answer for X is 1. The answer for Y is -10. The answer for Z is 7. 1, -10, 7. 1, yeah, because that would be 3 minus 10 is -7, plus 14, 7. So that would work here. 5 times 1 is 5. That would be 20 negative. And 3 times 7 is 21. 21 plus 5 is 26 minus 26. That works. And then 21 and 4 is 25. Yep, that works also. So I just checked by doing the computations in my head, and sure enough, that gives us the answer. Now, I just randomly came up with 765, but if you put 1, 2, 3, any number, all we have to do is multiply by the appropriate column, and we get the answer. So we can mass produce solutions for this system of equations by if we have different constants. All right, with this, we finished this video.